Welcome back to part 3 of 4 of our logistic regression demonstration. In this section, I'll show you how to interpret the interaction that we just added to our previous model. And you can see in this output that our overall model is still significant, which is encouraging. And you can see the interaction was added in that our degrees of freedom have gone from 2 to 3. So that reflects the addition of the interaction term. And we also see the reflection of the addition of the interaction term right here with the addition of 1 degree of freedom for this particular block. And we, on the positive side, find that the addition of the interaction statistically contributes to the model. And how we know that really is looking at our model summary here. We see our -2 log likelihood is about 27 points lower than our previous -2 log likelihood. And that's reflected here in our chi-square difference score. So that's really what we're looking at, and that reflects a significant improvement in our model fit from our previous model, the reduced model, to our full model. And we also have here our pseudo R-squares, which again, if you want to interpret, you need to do so with caution because they don't really map on one-to-one with R-squares that we get with OLS or traditional multiple regression. Next, we have another goodness of fit test, the Hosmer and Lemichaud test, and because we have a non-significant finding here, that indicates adequate goodness of fit for this model. And that is echoed in our contingency table here, where you can see the distribution, or our expected distribution across the deciles of risk, map on pretty well to what we observed in our data set. So that's also another piece of information supporting this model. Next, we have our classification table, and we see a pretty good prediction of the group assignment by this model at 81.2% correct. However, that's really kind of a nominal increase. Our previous model predicted 80.4% correctly, so it's not a huge increase in the predictive ability for this model, but it definitely is pretty strong prediction in terms of splitting between did not attend treatment and attending treatment. And here we have our parameters table, and this again reflects our dummy-coded gender, which, as you can see here with the indicator group being 1, which in our data set is men. And we can go ahead and look at both our statistical significance level for the previous variables that we had in the model, gender and center motivation for change, and their odds ratios, just to double check that they look around about the same. They don't have to be exactly the same. They'll definitely change a bit. But one issue that does come up sometimes with interactions, adding interaction terms to models, is that there can be some collinearity. So if you have any major sign changes or if certain variables become non-significant, then you do need to consider that as a potential issue to deal with. So here it looks pretty good. Then we have our motivation by gender interaction, and because again our indicator group is men, we're going to be interpreting this interaction for men. And we have our statistical significance level as obviously well below the 0.05 level, and we have odds ratio of 5.847. Now what this means is that for men, each 1 point increase in our center motivation for change indicates 6 times, or approximately 6 times, the odds of attending treatment. In order to get this the same odds ratios for women, you just go ahead and take the inverse. So to show you what that would look like, for example, for dummy-coded gender, instead of 0.105, I would say 1 divided by 0.105. And that will get us our odds ratio for women. So women are about 9.5 times, have 9.5 times the odds of attending treatment compared to men. So that kind of gives you an idea of how to do that. Now that's the quick and dirty way. If you want to get all of the statistics, which I would recommend, you can just very easily go into your syntax and change the indicator group, and I already did that here, but you can change it from 1, which was indicating men, just to 0, and you can go ahead and rerun that particular model, and that will give you all the same statistics, but just from the women's perspective as well. And here we have another table that shows the predicted probabilities. So 0.5 and below would be predicted as did not attend treatment, and 0.5 and above would be probability of attending treatment. And we can see here that our observed data points fall pretty well into this rubric. Most of the did not attend treatment folks are here below 0.5 in terms of their predicted probabilities, and most of our attended treatment folks are above 0.5. Now there is a little bit of mixing in there. You do expect that. You can't have perfect separation, but looks pretty good. And finally, we have our case-wise listing of the residuals, and this is really important to take a look at what your highest and lowest residuals might be. And I definitely look at residuals that are either below negative 3.3 or above 3.3. And the reason why is for samples that are less than 1,000, have less than 1,000 cases, usually you can use the p equals 0.001 level when you're looking at standardized variables. And what that would mean is that particular case, their residual is statistically significant from 0 at the p equals 0.001 level. And you do see that we have a few folks who have residuals higher than 3.3, which is some cause for concern if these particular cases represent outliers that have strong influence on the model. And you can look at that. I won't do that right now, but you can look at that going back into our binary logistic commands by saving your influence statistics here. For example, looking at which cases have particularly strong leverage, and also looking at how much the regression coefficients change if certain participants or certain cases are removed from the model. So that's important to look at just to gauge the influence of those residuals to see if those outliers are particularly influential. And if they are, you might want to consider either removing them, you can transform the predictor, you can consider adding other variables to the model that might help account for some of this extra variance. It really kind of depends on the model and what you're going for, but it's important to pay attention to those. And when in doubt, rerun the model without the outliers. Now, to get a good idea of how those outliers look and where exactly they are, what kind of characteristics those folks have, I like to graph them. So I'm going to reset this here. I just go into the chart builder, and I like to use the line graph here. I like the way it looks. And I put the center motivation on the x-axis, and I put the standardized residuals on the y-axis, and that's just the SPSS default name there. And you can go ahead and set the color for if you have a categorical variable in there. And that will kind of give us an idea, a visual representation of where our outliers are. And what we see here is that they are primarily men, so we're looking at folks who are below negative 3.3 and above about 3.3, like right in there. And we see they're predominantly men, well they are men, and they tend to be at the lower levels of motivation for treatment. So that's just something to be aware of, and it can kind of give you an idea of where your residuals might be off. And that is it for this section, and if you join us in the next one, I'll show you how to graph your interactions so that you have a nice visual representation of what we've done.